Jonathan. Our next speaker is Jonathan Frankle. And take it away, Jonathan.
Awesome. So, for starters, I just want to say this is joint work, and I really genuinely mean deeply joint work with Carolina Gigaite, Dan Roy, and Michael Carbon, my collaborators on this paper. This is really, the amalgamation of a lot of ideas from all these authors. So please credit where credit is due. The last presentation wrapped up with a little bit on neural networks, and we're going to go big on neural networks in this presentation. I'm an empiricist. I'm really excited about what we can see and feel and touch in large-scale systems in practice, and that's what I'm going to focus on today. So I'm going to try to give you a little bit of insight into the nature of the loss landscapes of neural networks, at least the way that I see them and understand them. So, let me just dive right in and start with a research question. No need to beat around the bushes here. Suppose that we start with a randomly initialized neural network, and we decide that we're going to train it, and we're going to train it, using two different data orders. So two different, in some sense, samples of SGD noise. What happens to these two networks, and how are they related, or how are they not related? To what extent does the SGD noise of these two separate data orders affect the outcome of optimization? This is really the question that I'm going to try to answer. So we have these two subnetworks. How are they related, or are they related? And what can we say about them? And what does this tell us about the nature of the stochasticity of SGD and the nature of the loss landscape for that matter? So here's one way of trying to understand the relationship between these networks. You could imagine a lot of different relationships. We could look at the functional behavior. We could look at the relationships between the weights. But in this particular work, and hopefully you'll see why in a few moments, we ended up deciding to look at the loss landscape that relates these two networks to each other. So, these two networks are just points in space, in this high dimensional weight space, and we can interpolate between these points linearly and try to understand the nature of the landscape between them. So, that just gives us another set of networks in between these two networks, and we can interpolate and look at what happens to the error or the loss as we interpolate between these networks. So you might expect to kind of see, and I'll show you in practice, you see two specific behaviors here. One behavior is you interpolate between these networks and you encounter a barrier. This is the common expectation. We're in a non-convex landscape, and these networks might be separated by a barrier potentially. SGD noise may take them to two separate outcomes, and that's that. Alternatively, you might actually expect to see that they're in the same convex region. That might be a little bit surprising. That might be, one might not necessarily assume that right off the bat. I'm actually curious to just let folks take a moment. Which of these outcomes do you expect? If I were to give you an ImageNet network and give you two copies and run this experiment, what would happen? I don't think we can do raise hands in seminar mode, but if I were giving this talk in person, I would love to do that and try to understand. Do you think that we'll see a barrier between these two networks if we train same network, same initialization point on two different data orders? Do you think we'll see a barrier, or do you think that we'll find the same convex region? And Wolfram, I'm seeing nodding and I'm seeing shaking your head. Do you want to chime in and give your answer here? We could do this seminar style a little bit.
I say it's flat. If you have enough hidden neurons, it's flat. That's my guess.
Okay. Anybody else who's a panelist here and can just hop right in? Anybody want to disagree? So, let's talk about this a little bit. So this property, and I'm going to define this property as linear mode connectivity, that the modes found by the networks are linearly connected if this property holds. Now, mode connectivity in general, let's take out the linear part for just a moment. This is an old concept in deep learning. And by old, I mean 2017 or 2018. So, this is deep learning where 2017 is ancient history and 1990 may as well have been the Stone Ages. But, in the ancient history of 2017, these two papers, which came out simultaneously, showed that if you take a network and you train it twice on two different data orders, in fact, if you start from two separate initializations, I've even simplified, I'm giving an easier case here, but even if you start from two separate initializations, you'll be able to find a path between the minima found by the networks over which loss and error do not increase on both the train and test surfaces. And in fact, this path tends to involve two, it's piecewise linear with two pieces. So if you do linear mode connectivity, if you try to linearly interpolate in a circumstance where you use two separate initializations, this doesn't work. I'll tell you that right off the bat. This is why they needed to resort to a piecewise linear, or in this case, a Bezier curve that I'm showing up here. And these are awesome papers. I highly recommend reading them. They were, a large piece of the inspiration for this work. So mode connectivity, we know we have. But linear mode connectivity, unclear. And, I still haven't resolved Wolfram's hypothesis yet and whether it holds true or not. So why is linear mode connectivity interesting? Why should we care about it? Well, number one, it's a stricter property than mode connectivity. Mode connectivity seems to just show up in general. On the hardest neural networks from 2 different initializations, you can find connected modes. Linear mode connectivity is stricter. Linear mode connectivity also gives us a lot of power. We end up with this convex region if we find linear mode connectivity. We can ensemble networks merely by interpolating between their weights or averaging the networks. It gives us some interesting room to play. So, and especially when we're thinking about a non-convex loss landscape, it's very interesting to understand the nature of convex regions that might show up and under what circumstances you might be able to find them. And I'll hopefully give you toward the end of the talk one other interesting reason why linear mode connectivity is exciting to me. And this is that it actually seems to say something pretty important when we get to sparse neural networks, which is really my area of interest. So, okay, let me go and make this question a little bit deeper. So let's suppose it didn't happen in initialization. Let's say that, Wolfram is wrong, and, I'm wrong, and this doesn't happen in initialization. Sorry, thank you, Wolfram, for letting me pick on you a little bit here. But let's suppose he's wrong and his hypothesis doesn't hold. This doesn't happen in initialization. When does it happen? So let me give you a different thought experiment. Suppose that I train the networks identically up to some iteration k. And let's say that k is the entire length of training minus 1 step. You would expect that if you train for that last 1 step with 2 different samples of mini batches, you'll probably end up in the same convex region. It would be very strange if 1 step was enough to send your neural networks off into different regions, especially at the end of training. So the question then emerges, where does this behavior transition? At what point do you transition from unconnected to connected? And why, and what does this tell us? And how does this happen? So, we can run the same experiment. And we can do the same thing, just instead of splitting at iteration 0 from the beginning, we split at iteration k. We train this one network until a certain point, and then we make 2 copies and train them on different data orders. And again, we can analyze the effect of SGD noise. This noise is really coming in some sense, at least from this perspective. You can think of the outcome as being a random variable that is dependent on the randomness that you inject into the mini batch order, the data augmentation in the case of vision networks, all the noise that supposedly helps to give us good behavior when it comes to SGD. Okay, so we can interpolate again, and we can, look and see what happens and analyze, the loss landscape. And, again, we'll see 2 outcomes. Either it's going to look something like this, or it's going to be flat. And generally, these are the 2 outcomes you see. I'll just go ahead and reveal that right off the bat. So really, here's our research question, fundamentally. And I want to keep this simple. I don't think we have to ask complicated questions empirically to get to interesting results. At what point in training does the outcome of optimization become determined regardless of data order, at least determined insofar as we consider being in a convex region to be determined? There are all sorts of definitions of determined you might come up with. This is the one that I'm saying by fiat is, an interesting one for the sake of this conversation. So you can run this experiment. The nice thing about this is that, for anyone in the audience who's literate in PyTorch or TensorFlow, I'm guessing you could code this up in a couple of hours and tell me what happens. If this talk were a little bit longer, I would pause here and say, let's come back in the afternoon and let me know what you find. But I'll cheat and I'll go ahead and let you know what happens. So let's look at some networks. And I'm going to focus on a range of networks. This starts in the upper left on Linnet and just an MLP on MNIST. MNIST being, at least as far as I'm concerned as an empiricist, the world's most trivial data set. You can, I think, as someone once told me, you could sneeze into a tissue and it would still be able to get 99% accuracy on MNIST. CFAR10, a little more challenging. And then ImageNet, which, is the entryway into the large scale tasks. At this point, it's more of an entryway and not the large scale task itself, but it at least gives us a lot of the challenges that come with that kind of behavior. And we're going to see what happens. So we're going to vary k all the way from 0 at the beginning of training, to some values pretty late in training, and we'll see when linear mode connectivity emerges. So, we'll find out when we go from this behavior to that behavior. And I want to give you one more just kind of quantity here that's going to be very useful in the long run. I'm going to show you a bunch of diagrams where I'll actually show you that interpolation graph, this kind of hill or this flat surface. But that gets really tedious and it's hard for me to vary k and show you that. So instead, I'm going to show you a quantity in many cases that I'm going to call the instability. This is just the height from peak to valley. This is the size of the barrier. The idea here is it just allows me to distill this graph into one number so I can show you things in a much more synthesized way. Okay, everybody ready? Any complaints, questions, fundamental epistemological complaints about empiricism? Okay, good. Here's what happens. This is MNIST on our MLP. I'm going to start here because this is pretty simple. So Wolfram's hypothesis, which again, thank you for letting me pick on you, is working great. You can see, I'm plotting the test error and the train error surface. Take your pick. This is error, not loss, just so things are kind of on scales that one can intuit very easily. And for this MLP on MNIST, you can see that starting from the same initialization, I'm training 2 copies from beginning to end. This is just from initialization for now. We'll look at varying K in a moment. Yeah, we find the same convex region from the beginning. And this is a result, lots of people have shown this in lots of different contexts throughout the literature. This, at least prior to this work, this was the biggest experiment anybody had run, in this style. But here's what happens on everything else. MNIST, again, as I mentioned before, you could sneeze into a tissue and be able to get 99% accuracy in MNIST. It does seem to be an easier task, at least with respect to this. Okay, we've got a question. How do we define the end of training here? We train from initialization until what condition? So I'm going to be a good empiricist here, and I'm going to say the end of training is whatever people normally do when they train these networks. So typically what you'll do is you'll train with a cosine decay learning rate schedule until the learning rate reaches some infinitesimal value, and that is when training ends. Now you could vary the length of training. You could, say, well, I want to train for 50 epochs or 500 epochs or 5,000 epochs. I've tried these experiments, basically running them, ad infinitum. For long learning rate schedules, you do always want to decay the learning rate schedule. And I can't actually tell you off the top of my head what would happen if you didn't decay the learning rate schedule. Typically, you'll get pretty bad performance, relatively speaking. So it's a less interesting outcome. I think it's a good question. But the stopping condition here is because Kai-Ming in 2015, who wrote the ResNet paper, said that we're stopping after 90 epochs on ResNet 50. And typically, if you train for longer, you don't get that much more performance, although some people train ResNets for much longer. It doesn't seem to make a huge difference for these results, at least in my experience. So this is what happens. And you can see we've got barriers across the board. And in fact, you can see all these barriers get flat at the top. This is because I'm measuring error. And so you reach the error of random guessing. On ImageNet, that's 99.9%. On CFAR10, it's 90%. So you can see that these graphs basically top out. In pretty much all quote unquote real cases, beyond MNIST, we don't see this linear mode connectivity behavior from initialization. That's the key takeaway here. And I think there's actually an interesting lesson that I take away from this, which is, everybody says MNIST is a little bit trivial, at least in the empirical literature. We frown on MNIST, and I've just disparaged it multiple times. There's a bit of a reason that we frown on MNIST, and it is that, this does seem to be an easier task. This does seem to have some different behavior empirically and scientifically from what we see at scale. And it's important to scale things up to make sure that, we understand behavior in kind of the practical limit. Okay, so no linear mode connectivity in general at initialization, at least beyond MNIST. And this is interesting. And there are certainly things we can do to the network to try to probe this. I've tried, for example, removing batch normalization from these networks, which, could have a factor here. I worked with a master's student on that. That didn't have an effect. So, we can hypothesize all we want, but let's look a little bit later in training. We're going to work under the assumption that if we go to, n-1 steps of training and then do the split there, we're going to end up in the same convex region. So there's got to be a point where this behavior transitions. That's the hypothesis that we have, or at least the supposition here. Okay, so at what point in training does this happen? This is our research question. Again, let's stick to our research question. So I'm about to show you a bunch of graphs that look like this. So don't read this data too much. This is just toy data, but I want to walk you through this graph before I show it to you, just so it's crystal clear what's going on here. So on the y-axis, I'm plotting the instability, the height of the barrier. On the x-axis, I'm plotting the iteration k where I make this split. So, for example, you can look at this particular point here. This is where I'm making the split at epoch 2. Training the 2 copies, and then this point here on the y-axis gives me the height of the barrier. Okay, everybody comfortable with this so far? Because I'm about to throw 5 graphs at you that look just like this. Okay, let's start with 1. This is our old friend MNIST. You can see that no matter when we split, we always find the same, the same outcome essentially. There's no barrier. Okay, good so far. MNIST is MNIST. I won't give you my metaphor again, but you know what I think of it. Here's what happens in all the other cases. And this is kind of cool. Okay, so I want to just give you a moment. Take a moment and just look at these graphs. You'll see for the CFAR10 networks, for the ImageNet networks, you'll see what happens here. I'll note that I have not plotted all the way to the end of training. I'm just plotting focused on the very early part of training. I'll give you some stats on that in a moment. So just take a moment and process it. Okay, so let me give a little bit of color here. So I'm going to focus in on, let's say ResNet 20. This is kind of my favorite. I would consider this the lab rat of neural networks, as it were, in terms of empiricism. This is my favorite little lab rat. Perhaps ImageNet is the chimpanzee that I'll test the pharmaceutical on as soon as it works in the lab rat. But this is where I like to begin. And I'm only showing you the first 10,000 iterations of training out of 65,000 here. I'm zoomed in on the very beginning of training, and this is a logarithmic axis. We reach linear mode connectivity. If we split at iteration 2000, we'll find the same convex region regardless of the data order, regardless of the SGD noise from this perspective, which I find really remarkable because it's only 3% of the way into training. After 3% of the way into training, the outcome of optimization is determined, at least up to linear mode connectivity. That to me was a little bit surprising. On this VGG network on CFAR10, it's again about 3%. For the ImageNet networks, it's closer to 10%. We're training ResNet 50 on ImageNet for about 90 epochs, Inception for about 180 epochs, so around 10% of the way into training, SGD noise doesn't affect the outcome anymore, which I find really intriguing. I don't have a profound thing to say about what this means about the fundamental nature of deep learning, but I take this as very surprising given the pedestal that we put SGD noise on and the importance we attribute to it. Maybe it's only the magnitude or distribution of the noise that matters at this point, and not the actual specific sample of noise that matters. But it is interesting to me that there's a phase of training where the sample of noise matters, and a phase of training where the sample of noise doesn't matter. So I find this very interesting. Now, I want to ask an even more fundamental question. We know that the outcome is the same, at least up to linear mode connectivity. What about the path? Are these networks literally following the same path along the optimization landscape? So the idea here is let's take the state of the networks at some iteration t, any iteration t after we've split them, and just interpolate their states at that iteration t to see, are they in the same valley? Are they following the same river through the optimization landscape? So let's look at ResNet. Let's look at VGG. These are actually sparse networks, but it doesn't matter. You'll see the same behavior in dense networks. And what I'm showing you is the x-axis is over time. So, and the y-axis is the barrier over time. Each of these lines is a different value of k, so a different point of splitting. So let's look at the left here, and you can see that blue line on the top. This is if I split the networks at initialization. You can see very quickly they diverge in their paths. There are barriers that emerge between them, and these barriers become, quite large by the end of training. As you increase the value of k, k equals 50, the orange line, these barriers diminish, and they diminish, and they diminish, until, in this case, about k equals 500. If for the sparse networks. It happens a bit earlier for the sparse networks. I'll tell you about that in a moment. You can see they basically follow the same path all the way through training from that iteration k up to linear mode connectivity. The sample of SGD noise doesn't even affect their paths very much, at least up to this metric. Now we can debate the significance of this metric, and I think that's a perfectly debatable question. I'm open to various critiques here. It does clearly seem to be a metric that is not overly inclusive or overly restrictive, which I think is also interesting and useful. And the same thing for VGG. You actually see this interesting liminal case with the brown line on the right, where there's a slight barrier that emerges and then disappears, which I think is really interesting. It's kind of cool to catch the network in this transitional state. But these networks are following the same path. That's essentially so I'll pause here again just for one moment to take in this data so that I'm not talking over you. Okay, let me move on a little bit. I want to tell you one last interesting fact. We're already running out of our time together, and I want to leave time for discussion, questions, and really ideas, because I think there are more questions than answers from even this very simple experiment. So I'm really interested, actually, there are a couple questions here. Let me address them before I completely change gears and talk about sparsity. How is the number of iterations into training before the zero barrier dependent on your initial learning rate? And what optimizer is used for these results? So the optimizer that I've used for these results is whatever was standard for the network. For the ResNets, it tends to be SGD with momentum. For MNIST, it tends to be Atom. For inception, I believe there's an exponential moving average and eta grad, I want to say, but I used whatever was standard. Personally, I'm really excited most about whatever people are doing in practice. I think the things that work in practice are this magical little island of stability in a world of neural networks that are completely useless. And so I'm very excited to understand that island of stability better and try to make sense of what happens in practice. Personally, for me, theory is less appealing because we don't yet know how to describe what separates that little island of stability from all the other bad, broken neural networks in the world. But this is just a personal bias, which is why I do empiricism. How is this affected by learning rate? If you increase the learning rate, this happens later. That's been my experimental results, which shouldn't be surprising to you. Increasing the learning rate is in some sense increasing the extent to which variation in the data order can affect the trajectory of the network. Let's see, we've got another question. For a given network and data set, might there be any tricks to making the instability curve decay even earlier? Thus far, the answer is decrease the learning rate or increase the batch size, things that should naturally affect the extent to which should either reduce the variability between batches, that is increasing the batch size, or should increase the extent to which the variability can affect the outcome of training. Things like learning rate warm-up also have an effect here because again, you're kind of decreasing the impact that variability can have early in training. Beyond that, I don't have any answers here, but oh, and we have instability as the middle point of training or the supremum, it's the supremum. So I'm looking at the highest possible point. Okay, I want to move on very briefly to sparsity because this is, part of my argument for the significance of this. In some sense, the presentation that I'm giving you is backwards. All of this work started from my look at sparse neural networks with Carolina, Dan, and Mike, and this property emerged as something significant in telling us the nature of sparse networks. So I won't go too far into the details, but my main research is about trying to find networks that from an early point in training could have trained on their own to completion, despite the fact that they were sparse and had, let's say 10 times fewer parameters than the typical dense network. These networks are a little more fragile. They're, a little bit flakier. They're a little bit easier to knock off track. And so what I'm showing you here on the x-axis isn't just the iteration k where I split the networks, but also the iteration k in which I create a sparse network, in which I sparsify the dense network. So you can imagine I'm training dense until iteration k. I'm sparsifying using an oracle, and I won't tell you the details of that oracle, but it's an empirical procedure. And then after that, I'm training those two copies of the sparse network to completion. So for the sparse networks, these are some scenarios I've concocted where we have linear mode connectivity from the beginning and from any point. And you can see, low and warm up here. These are cases where I played with the learning rate schedule, as I mentioned before, to try to induce linear mode connectivity from earlier on by way of a point of contrast. What I'll show you on the right here, this is what happens to sparse networks, and the sparsities are in the upper, or the densities, the number of weights remaining is in the upper right. These are kind of extreme sparsities that you can't accomplish trivially by just randomly pruning. That actually takes some work on the oracle's part. And you can see again the same behavior. And there's something interesting. So, we start off unconnected. And suddenly we see this phase transition very quickly where the networks become linearly connected and where instability plummets to 0. And this happens even earlier in training. Now for the sparse networks, this is 1.6% of the way through training or 5% for ImageNet. So this property, sparsity, seems to be a way of inducing this property earlier to answer one question. Now the cool part here is that sparse neural networks are hard to get to train accurately. What I'm going to show you on the bottom is the error of these sparse networks. Same sparse network and the error. The gray line here is the error of the unpruned network. The idea being that, this is the best that the sparse network could do is matching the performance of the dense network. And what you'll see is something really cool. These sparse networks don't seem to perform all that well until they also achieve this linear mode connectivity property, until the outcome of optimization becomes determined. If you create a sparse network at the time when the outcome of optimization will be determined, it suddenly starts performing really well. This is to say, these sparse networks in particular are very sensitive to SGD noise. They're very, as long as optimization can send them off on a lot of different trajectories, it seems it's likely to send them off to a bad outcome. They're likely to get stuck somewhere. So this is one argument that I'll make for the significance of this linear mode connectivity property. It tells us something pretty fundamental about sparse networks. It tells us something, it seems to be an indicator. It seems to be a signal, or at least it correlates with when these sparse networks start to do well, at least for the oracle that I've created to do this. So this is, the connection between sparsity, the loss landscape, linear mode connectivity, and an argument for the significance of this otherwise arbitrary seeming property. So I want to wrap up by going over the research question one more time, and then I'll go back, stick this data up here, and we can discuss questions for a little bit, because I think there are more questions than answers from even this very simple experiment. Our research question was fundamentally, at what point in training does the outcome of optimization become determined, regardless of data order? And the answer was early in training, if not at initialization. And at initialization, we can induce it by either making the task really easy or making the learning rate schedule such that we can induce this property, at least in the sparse context. But in general, for the kinds of settings that people really seem to train in practice, with aggressive learning rate schedules and what have you, it seems like it's early in training, but not at initialization. Early in training enough to be really intriguing. And I think, it would have been a boring result if I said it only happens at the beginning or end of training. This is exciting because it happens at this place that is early enough that the network hasn't reached full accuracy. It still has a long way to go in terms of learning and a long way to go in the optimization landscape. It's only in terms of actual, L2 distance traveled in weight space, it's typically traveled about halfway or less by this point in training, which suggests to me that there's still a lot of work this network is doing between these points. So significance, why should we care about this arbitrary property that I made up about half an hour ago and then quizzed Rolfram on? What is the significance of SGD noise if it doesn't affect the outcome of optimization? I think this really focuses in our view of the nature of the kinds of paths neural networks can follow and the nature of the kinds of optima they can find, but it doesn't seem to actually materially affect which path itself if you were to take, 2 samples of noise from the same distribution. So this should give us a little more confidence in some of our, assumptions about the role of noise in affecting the kinds of optima we can find. Really, I think the coolest part is, what does this tell us about the phasing of training? This really seems to delineate 2 phases of training, almost this explore and exploit phases of training. The first phase being where the outcome is undetermined and the network could end up going to a lot of different destinations. And I would call this, roughly speaking, explore, although the RL folks in the audience may yell at me about the imprecision of and co-opting their terminology. And then after that, it does seem like all that's happening is exploitation. The network is following, a trajectory that is determined at least up to this particular distribution of noise, if not this particular sample. And I think this final question is really interesting to me. I love sparsity because it makes everything a little bit harder and often surfaces weird pathologies that don't happen in practice with our very nice, very carefully tuned, very well curated neural networks. But you just make the task a little bit more difficult using sparsity and reduce the dimensionality a little bit, and suddenly these weird pathologies show up. And one of them is that sparsity can find both bad and good optima, depending on how you initialize the network and depending on, when in optimization you create it. And so this intimate connection to sparsity perhaps is telling us something a little bit more fundamental about the nature of optimization. But I'll speak in generalities here. Let me go back to the slide with the data so that we can have a discussion from here. But this is what I have. These are the results. Other folks, I think later today, you'll be hearing a little bit more about some other observations on linear mode connectivity, but hopefully this is a nice rudimentary introduction with some intriguing questions for further discussion. So from there, I'm happy to take questions from the audience, and there are several questions lined up here. So let me go ahead and start answering those. Thank you. Let's see. For small k, do you find rare occasions that instability is reducing? By reducing, I expect you mean that as you increase k, instability goes down. I think other than that one scenario I showed you for VGG, where the network seemed to kind of get separated by a small barrier and then come back together, I haven't seen any examples of that. Usually as you increase k, instability goes down. Let's see. Did you check any similarity measures between the 2 networks throughout training? I mean, to check whether they're really changing together in the same path, in addition to checking instability. So if you go to, I think it's Appendix G of the paper, you can see a bunch of different metrics for the end of training. These are things like looking at various notions of functional distance. This is looking at things like L2 distance. And what you'll generally see is a lot of these metrics tend to decrease in a correlated way with these networks, although the frustrating part is a lot of them don't go to 0. It's not like the networks find exactly the same point. And this was a major sticking point for reviewers the first 3 times this work was rejected, because the metric didn't go down to 0, and so the significance was unclear. The linear mode connectivity property was a good way of showing that these networks were intimately related without having to show that, for example, the L2 distance between the networks went to 0, which can be a little bit difficult, or the functional distance even went to 0. These networks are functionally distant, and there's follow-up work showing you can actually induce diverse functional behavior in the networks and still get them into what is effectively a linearly mode connected space, up to some very small amount, epsilon level of noise as you interpolate between the networks. Are deep networks more stable than shallow but wide networks? Can something be said about the dependence of the architecture on K? Not that I've seen so far. I did try an experiment where I took a ResNet and just widened it and widened it and widened it, and it didn't really affect the iteration K. So that was unfortunate. I was really hoping that, maybe in the infinite width limit, you would expect things should, maybe be stable from the beginning based on theoretical results or theoretical intuition. I didn't find that to be the case for the widest networks I could at least fit onto one GPU. That's not to say this doesn't happen, but it may be that, getting close enough to infinity for us to be able to, mirror what we might expect in theory requires more than one GPU. But, I think it's an interesting experiment, but empirically, it's not something that I saw. Do we know if the low instability is because the networks converge to the same basin in terms of the permutation symmetries, or could it be that one can interpolate between different symmetry-induced minima without incurring instability along the way? I would say wait on that question, because I believe later today you'll be hearing about that in a lot of detail. So, I hope that is a nice appetizer for a talk that is to come. What do you think of sparsity by inducing flatness and its relation to smaller Ks? What do you mean by inducing flatness? Raheem, you're here, so you can just feel free to hop on, turn on your microphone, and let's have a conversation.
Sure, thank you, Jonathan, for such a great talk. So by inducing flatness, I mean, like, we know that sparsity helps generalization, right? By finding solutions which are in flatter regimes. So my intuition is that, like, sparsity helps finding such solutions. And this helps to find smaller Ks. So the reason that we are finding smaller Ks in your experiments is that we are finding solutions earlier, like in the ultimate basin. We are finding this ultimate basin earlier in training.
So I think that's a totally reasonable hypothesis. I have no evidence to contradict that. My intuition and my hypothesis is that by sparsifying the network at an early point in training, we're simply reducing the number of degrees of freedom. And there are fewer opportunities for the network to get thrown off of a particular trajectory. And so this happens a little bit earlier because, in cases where the noise isn't going to take over, the network really doesn't have as many degrees of freedom or as many dimensions in which it can wander off or be thrown off. But again, that's just a high-level intuition. And I think these are great hypotheses. The proof is in the empirical evidence. So we'll need to come up with an experiment to evaluate this.
Okay, cool.
Let me go through the last two questions I see up here and then, give the panel a chance. And I also want to give Wolfram a chance to respond now that I've thrown him under the bus throughout the entire talk. Thank you for being such a willing participant.
I also want to remark on some of the questions you asked.
Awesome. So why don't we go to the panel for a little bit and then we can go back to the questions in the chat.
If I may go first, or you want Wolfram?
Oh, no, go for it. Go for it. Wolfram, I'm not assuming you even have any questions, but I appreciate your being a strong man throughout the presentation. I'm very grateful.
Now, at the end of your talk, you mentioned that why do we care about the noise in SGD if it just matters at the beginning? I mean, so from what I understand, the way you think about landscapes is that you fix the architecture, you write down a loss function, then you get a landscape. Is that correct?
That's correct.
And you talk about initialization, and then the way you run the algorithm. So all of these plots does some variation along this theme, right?
Yep.
Now, so then you argue that, well, in the end, maybe the noise in SGD doesn't matter because they all seem to be going to the same place and get well-connected locations, right? So the noise in SGD would matter if you want to avoid things like saddle points. So initially, if your landscape has saddle points, the noise would matter because you want to basically have a way of getting out of let's say these traps, okay? So on that front, the noise in SGD is critical. Otherwise, you would be stuck there. No.
So I agree with this. I think it's more of a straw man argument to ask, why does SGD noise matter if it doesn't affect the outcome of optimization? And I completely agree with you as to the answer. I think this should focus our intuition on the fact that SGD is not really doing very much exploration of the space necessarily. There's a point early in training at which the outcome is determined. So the exploratory part of SGD is probably not as important as the ability of SGD to keep you out of saddle points, keep you out of bad minima, keep you from getting stuck. So this should basically confirm or reaffirm, I would say, that intuition or that belief about the role that SGD plays or the role that stochasticity plays.
And then given the initialization, you can show that the Hessian of the network has some convexity. If you are doing proper initialization, hey, or whatever, Xavier initialization. In that case, if you actually end up landing in a convex basin, then yes, the SGD noise wouldn't matter. So on that front, do you actually have, I mean, have you looked into maybe the hashing of these loss functions that you're looking at, for example, so to respond to your own questions?
I haven't looked at the Hessian as of yet, but other folks have. So I defer you to other people's work where people have looked at this in detail. I don't recall how exactly that will correspond to this particular set of results, though. So I would say I'm not the expert to ask on that particular question. Because
if the problem, the way you set it up is convex, then some of these questions could be answered in a straightforward manner, I think. Anyway, I'll defer to.
So I would work under the assumption the problem is not convex, given that we can end up in so many different optima.
I think that the way the problem is set up, it is definitely non-convex, but the way you choose the architecture and the initialization, you can actually prove that with high probability, you will end up in a convex basin. This is the kind of results people in overparameterization has.
Okay, I won't disagree with any of this. Okay. Happy to have a conversation about that.
Sure.
Other questions from the panel? Okay, let me go back to the chat then. Let's see, you talked about the impact of different learning rates. What's the effect of batch size? Batch size and learning rate are, at least for the purposes of this particular experiment, relatively interchangeable. That is to say that, as you increase the batch size, it has the effect of reducing the variability in the outcomes of training. And so you'll see a similar effect. If you were to increase the batch size, you'll follow a similar path and end up, and your iteration K should get earlier. And that tends to fit with the empirical results we have, where batch size and learning rate, at least in the computer vision context, tend to be proportional to one another. Let's see, does increasing sparsity means instability goes down earlier? That is there a linear relationship between increasing sparsity and decreasing the time at which the switch to instability happens? A little bit, if I recall correctly, but it doesn't actually seem to matter that much. The sparsities I'm showing here are the most extreme sparsities where we could find networks that matched full accuracy. So this is kind of the most difficult possible scenario. And I believe that as you add more parameters, using the word increased sparsity is very confusing. As you have more parameters in your network, you will end up interpolating between this behavior and the behavior on the dense networks. That is to say, you will end up, the iteration K at which stability happens will happen later and later and later in training, up to the point that I showed you for the dense networks. Okay, I know we're running out of time. Let me try to get through these last couple questions. Are your networks sparse at initialization and trained from there, or do you prune along the way? So I'm using a technique that retroactively prunes. I train the network to completion, I prune, and then I use that as an oracle and say, if only we had known at the end of training these weights would be unimportant, we would have pruned them earlier. And then I go back to an earlier point in training and prune those same networks. And I'm pruning those same weights at different iterations K. So what you see in the graph where sparsity happens is, or what you see in the graph for iteration K is both where we split and where we sparsify. Does sparsity benefit to a ConvNet which is already sparsified by weight sharing and small receptive fields? Oh yeah, I mean, you can see the sparsities up here. For VGG, I'm pruning to 1.5% sparsity and we're losing no accuracy. So this is an old result that goes back to before I or many of the folks here were born in 1989, but we know that we can sparsify even networks that have parameter sharing. Could you generalize your approach to investigate the way networks diverge if they're trained on two data sets that come from slightly different distributions? Yes, you could definitely do this. And I believe someone has done this. I don't remember the context, where you actually, some papers that predate this work have actually looked at this experiment for MNIST, where you train on two different subsets of MNIST after the split and then interpolate to try to understand how the data distribution might affect the outcome of training, or at least how the sample of data might affect the outcome of training. And you could easily imagine doing this for, two separate data distributions, or taking data from yesterday and data from today if you were looking at a recommender system. So I know we're at time and I want to make sure that we don't run out of time. So any last comments or complaints from the panel?
So I think
awesome. Thank you.
In the interest of time, Jonathan, thank you for your talk. Let's thank Jonathan again. All right, perfect.